Hi, my name's Steve Huber. I'm the founder of a startup called Redwood EDA. In today's tutorial, you'll get a chance to work on components of an actual CPU core that you build. You'll be able to see your core running online in simulation. And in doing so, you'll learn a number of really exciting technologies. You'll learn about RISC-V instruction set architecture. RISC-V obviously is very hot these days. You'll learn about the Makerchip.com online IDE platform offered by Redwood EDA for circuit design. You'll use that platform using transaction level Verilog, a next generation Verilog language extension. You'll be implementing combinational logic to complete the CPU core, and you'll be able to see that core running online. Let me jump now to a view of a program running in a CPU core. So a CPU is responsible for executing a program, and that program lives in instruction memory. At the end of the day, it's just ones and zeros. The CPU will access instructions and interpret those bits of the instruction as machine instructions. In this case, this machine is fetching the first instruction from instruction memory, which is an add instruction. And the first thing the machine needs to do is interpret that instruction. And here we have instruction decode logic, which is interpreting the bits of that instruction as an add. It's recognizing that that add is taking two values and producing a resulting value. And those values it's getting from a register file. The register file in a RISC-V machine contains 32 register values. And this particular instruction is accessing two source register values, both from R0, which has a 0 value. So we see those zeros in R0 that the machine has grabbed to execute this add instruction, and it's producing a result that it writes into register 10, which is a 0 value. Now let's step that machine forward, and it's going to then fetch the next instruction. So it fetched this second add instruction, which is getting its source values from register 0 and register 10. It's loading those values from the register file, performing an add. 0 plus 10 is 10. 0 plus 0 is 0. It's writing that 0 back to register 14. And we'll step again. The next instruction is an add immediate. It's taking a source value from register 10, which in this case is 0, and adding a value in binary of 1010, which is in decimal 10. So it's producing that 10 result and writing that back to R12. We'll step this again. We have another add instruction that's also grabbing 0 values and writing a 0 result. And step again. Another instruction also operating on zeros, not very exciting. The next instruction is an add immediate, which is operating on a 0 and adding a 1, producing a 1, writing that to R13. Stepping again. So this instruction is a branch instruction. And this branch instruction is, it's a little confusing to look at this string of ones and zeros, but this is actually a -2, -2 instructions in any case. So that's going to jump us up in our program 2 instructions earlier. So the branch instruction itself is a branch less than. It's taking these two source values, a 1 and a 10, and comparing them. In this case, based on the comparison, the branch will be taken. And if I step, we can see the program counter, this represented by this arrow, jumping up 2 instructions and then refetching this add instruction. So what is this program doing? This is actually the program that we'll be using throughout this tutorial. You'll be building the CPU core and seeing this behavior once you build your CPU core. We are in fact inside the Makerchip platform right now, and you'll be learning more about this platform soon, but right now we're just looking at the visualization of the CPU that you're going to be generating. And this program that we're going to be executing with your CPU is summing numbers from 1 to 9. And we've just gone through the instructions that are setting up the loop that we're going to iterate over that's going to sum the values. And we just did our first iteration of the loop. And that iteration loaded this value of 1 into R13. And then it added that 1 to R14 to get 1. And you'll see as we step forward in this program, I'm going to just continue to step instructions. And if you look at R13 and R14 as I step instructions, you'll see that R13 is incrementing by 1 with each iteration of the loop. 1, 2, 3, 4, 5. And for every count, we're adding that count to R14. So stepping back, I'll just jump to cycle 0 and start iterating again. If you watch R14 now, you'll see that R14 keeps adding that value from R13. So it added the 1, it's going to add 2 to become 3, it's going to add the 3 to become 6, it's going to add the 6 to become 10, and so on. And we can see that adding numbers from 1 to 9 results in a value of 45. So just stepping back a second, what you've seen at this point is the CPU, or rather the instruction set architecture. And in this case, we're looking at RISC-V, roughly speaking. So you've seen that a CPU core is responsible for fetching instructions from an instruction memory, executing those instructions one by one, and exchanging values with a register file. The CPU core also has access to memory. We are not in this tutorial going to use memory. Our program operates entirely out of the register file. All right, so I'm going to, let's see, jump back to the slides.